Now, maybe? I don't know. Is this thing working? It's recording. All right. What's going on, ESYST-101 fam? For those of you who cannot be here, we have a small but mighty subsection of our ESYST-101 Fall 2020 course, and we're going to take on this monster. I want to give some preface to it. I had a previous student who said, hey, I looked at this YouTube video about a a parallel series combination circuit. She went through it. I didn't understand a word of it. Of course, the first thing that went through my mind is, why are you watching a tutorial video after you took my class? That's neither here nor there. Secondly, I want to break it down and see if we, fall 2020, can knock this thing out. I think you're going to be superior to previous classes. I just got a feeling. So, guys who are here and joining us tonight, guys and gal, excuse me, everybody, I'm respecting everyone's pronouns. We are going to do this together. I want everybody to jump in and be able to contribute. This is going to be, I think, not nearly as hard as we think when we're looking at it. And we've got just under 30 minutes, oh, just over 30 minutes to knock it out. So, our ultimate goal. We want to know all the things. I want to know every voltage drop going across each resistor. I want to know amperage at every wire. I want to figure it all out. And the only thing that we do have in our knowledge toolkit right now is the voltage source, which is 20 volts, and then the values of all the resistors. Our first goal will be to, anybody want to hop in? What should we be trying to do?
Simplify everything?
That's right. We're going to simplify it. We want to try to take this entire huge combo monster Godzilla circuit and break it down to a single circuit with only one resistance value, one voltage source value, and from there we'll be able to discern the current. So that means our initial goal will be to get the total resistance of the circuit, because a total resistance of a circuit can be found by adding up the sum of resistances in a series circuit, and then from there we'll be able to use Ohm's law to get the total current. I would like to hope that those who are joining us have my cheat sheet. Does anybody not have my cheat sheet handy? I'm going to try and hold it up real quick so you guys know what we're looking with. It's not that one. I don't even have it handy, so I guess that's pretty telling, right? Oh well. All right, we're going without a cheat sheet. I know that the course will work itself out. Okay, so first things first, here we go. This is a sheet that I'm hoping everybody has handy. Solid, Richie's got it. I know everybody that doesn't have their camera on is holding it up to the blank camera, or the camera that doesn't exist. Pam's got it. Everyone's got it. All right, solid. Let's do this. Okay, so first step, we want to break this down to the most simplified component, the simplified representation of the circuit. Let me switch over to something we can play around with, and I will then let you, guys and gal, drive. All right, oops, I gave away something. I'm going to delete this. Is it too late? I'm going to remove this. All right. I'll give you a hint. The first thing to do would be to make the simplest breakdown that we possibly can. If I were to make a suggestion, if I could be so bold, and I will let you guys go from here. Yeah, I'm in the right place. I see an excellent candidate in this branch right here. Has two resistors in series that we can make into one, but I digress. I will let you guys take it. How do you want to do this? I'm just going to start calling on people. Dustin's got it. What you got, bud?
We can do the same way you did to simplify the how do you want me to how to do it? Like, well, you take. I think we should do the parallel one, the 3 and the 5.
Okay. You want to do the parallel one first?
I mean, the series would be easier, but
Okay. You want to do the series one first? All right.
I'd rather do the parallel one. Let's do the hard one.
You want to do the hard one? Shh, I like where your head's at. Okay, I'm going to draw up both branches that I just identified. We're going to call this one 15 ohms. This is R1. R2 is 2 ohms. And then this is the A branch, and I'm going to reproduce the B branch right here. And that's going to look like 6 ohms, and then one naughty parallel branch, which is 3 ohms, and 5 ohms. All right, so you want to start with the parallel branch. I like where you're going with this. Let's knock it out. So, how do we break down a parallel resistor branch into something more simplified?
1/3.
1 over 3, like that?
Yes. Plus 1/5, because you
Ooh.
do one over each uh, uh whatever resistor in the circuit, the parallel circuit, then one over everything.
And then, okay, so got it. Like that?
Yes.
That is 100% accurate. Oh man, you're already knocking it out. Okay, so what does that deduce down to?
1.88.
1.88, and we'll respect the the nomenclature, so that's an ohm right there. So we've
Yes.
actually just taken branch B, which was resistors, I believe 6 and 7. R 6 and 7 is equal to 1.88 ohms solid. So we can actually take this guy. What is going on? Why are you doing that to me? There we go. Okay, excellent. All right, so now we actually have two series circuits. Oh wait, I think we still have a parallel circuit. All right, so what's next? What are we going to do next?
Then we can simplify the series ones, well, either one,
Okay. We could
and
do we'll knock them both out. So let's simplify these. Let's say branch A is now 17 ohms and branch B would now be 7.88
7.8.
ohms.
Yes.
Is that right? 7.88 ohms. And as we're going through this, I should probably keep better track of it, but we're gonna keep this in mind as we start blowing it up at the end. Um, we created a circuit that now looks like this. I'm gonna try to erase this to give it some more perspective for you guys. So we've got 10 ohms here, and a resistor there, and a resistor here. So we still have a series and parallel circuit, but that's not a problem. So how are we going to knock this last part out?
Um. Uh. I am be honest, I probably forgot about that last time. So.
Not a problem. Okay, so we still have actually a parallel circuit here. If we want to make a series circuit, which is ideally the most simplified circuit, it's all the resistors in a line. So if we can find a way to collapse these two down, we would actually have another series
Uh.
circuit. So let's start with that. Does everybody agree with that?
Yeah.
All right. So,
So you'd use the same formula as last time as doing the parallel circuit, correct?
precisely.
Perfect.
You guys are on top of it. Now, I want to show you another version or another representation that this looks like. So if we're looking at,
Wouldn't it be the 1.1 over 17 and the 1 over 7.88 as opposed to 1 over
Yeah.
10 and 1 over 17?
oh yeah, excuse me. That is absolutely right. Yeah, I erased that number, 7.88. Thank you so much for pointing that out. That's 100% right. So this representation, if you ever see this, you won't see this in this class because I try to keep it simple for you, but this is the same as writing, whoops, writing this to the negative power. But I feel like that confuses students every time it's written that way. So I'm going to leave it in a standard format. So let's before we get onto that, for those who can't join us, if you were to put this and try to throw this calculation into Google, how would you do this in the Google calculator? Remember, we got to separate things. So it's essentially creating groups everywhere you see them. So it would be the equivalent of if you threw it just in the search bar in Google 1 and then one big group here. Oops. 1 divided by one big group, and that group would be 1 divided by 7.88, close that group, plus this 17 ohm resistor is another one, so 1 divided by 17, and then finish that group off. So essentially, for every resistor that in a parallel circuit that you're trying to solve for, you would just create a group and add them. Throw the values of that resistor in there, group the entirety of it, and divide it by 1. Did I go too fast there? I'll do it one more time really slow. So we have a parallel resistor, a parallel circuit, and it's got 2 resistors. We know that we're going to have 2 resistances that need to be grouped and added together. The resistance values are the denominators, so 1 divided by 7.88, that's real small. 1 divided by 17. But all of this in the denominator is a group itself, so we're going to throw parentheses around that. Then divide
5.38.
5.38, it's 100% accurate. Right, so what that looks like is finally we got an inkling of a series circuit. 10 ohms at the top, 5.38 ohms here. Alrighty. Really quickly, who remembers what the value was right here at this parallel circuit?
Which one?
Wasn't it like 7.88 or something?
Let's see. I don't have.
I have it all.
Let's see. I think I wrote a note down. Yeah, I think you're right. 7.88. I'm gonna score this off to the side so we know what that was. Oh, you know what? I think it was actually 6.88 because we added.
No, it was 1.88.
1.88. Yeah, 1.88 because we added 6 volts to it, or 6 ohms to it. So 1.88 ohms is that section right here. Okay, so we have a series circuit, and we know that it's a 20 volt source. I think we're ready to simplify and get the total current. Am I right?
Yes, sir.
Okay, so what is going to be the next step?
You add the currents together. I mean the ohms together.
Okay.
Current, and then it's going to be 15.38.
All right, 15.38. So we know that our total resistance for this bad boy, let me get rid of this, throw it in red. RT for the circuit is equal to 15.38 ohms. Our voltage source is equal to 20 volts, which leaves our current to be, and Ohm's law can help us out with this one. Really quickly.
0.76
or 1.3.
Oh yeah, one.
Well, let's do it for everybody who's not as astute as you guys might be. So VIR, we're going to replace where we can. 20, we are looking for the current, so we're not sure what that is yet. And then our resistance is 15.38. And I believe the way Dustin, don't let me put words in your mouth, but the way you got this was you divided 15.38 from both sides.
Yeah.
And that left you with the current being 1.30 amperes. Is that right?
Yeah.
Solid. Okay, so we actually have solved two of our three goals, which was find the total resistance, and you guys nailed it, and also find the total current. And that was no easy feat, but you rocked it. So I think with the current knowledge that we have now, we could pretty much apply Ohm's law to any portion of this circuit and expand out. Let's see. Okay. So how shall we proceed? Let's here, let me give you a little bit of a starter. Does that sound good? And please, if there are any questions, if anybody wants to stop the bus right now and we can go back a little bit, let me know. I don't want to walk too far. Any questions? Nope. Okay. All right, so I'm going to redraw a section of the circuit. And I hope this might help. I'm going to expand one out. The last contraction, the last condensation that we did was we took a series circuit, and we made a one resistor simple circuit. So I'm going to take that out just a little bit. And I believe this was 10 ohms. And when this was condensed, it was 17 ohms. Is that right?
Are you doing both A and B branch together or just A?
I'm going to do both of them together. So that would be 5.38 ohms. 5.38 ohms, right? Because this is that parallel circuit condensed, this section right here. Does that make sense? What we're actually looking at in this phase is the last thing that we did was we collapsed this parallel branch into this single resistor. So now we're going to pop it back open. But before we do that, we want to find the voltage that's going to flow through those rails. But really quickly, stop me if I'm going too far. I should have done, instead of erasing it, I should have kept each phase alive. But let me go back. So we've condensed everything to one resistor in order to get the amperage. Now I've broken that one resistor into the two resistor series circuit that we just had. That was 10 ohms at the top, if you can see that right here, and then 5.3 ohms on the side right here. But this 5.3 ohms or 5.38 ohms was actually a parallel circuit that we condensed. Do you guys remember that part? Okay. Here, let me help jog some memories. Before
If
we,
you want to help identify it, you could put that that's branches A and B condensed.
yeah, exactly. It's a great idea. AB. That's what this guy is. This rail is essentially AB. But if we were to extract it again, it would have been 17 ohms plus on one branch and 7.88 ohms. That's what we did to condense it in to make it a series circuit. So what we want to do, I should have left that there, I'm sorry. Let me put that back for you guys. What we want to do is we want to find, now that we know the current going this way, we want to know how the voltage drop is going to occur, because voltage in a series circuit, let me point you to your little cheat sheet here. I believe it's the third bullet point where it says series circuits. We have different voltages across resistors in a series circuit, right? We're separating the pressure based on the resistance in a series circuit. So the question that I want to answer is, how much voltage is dropping across this resistor, vice across this resistor. Because in reality, what we're looking at is the voltage that's going here as opposed to here and here. We can do that with Ohm's law. If we want to find this is R1, but I'm going to say we're looking for V1 right here, and here we're looking for V2. If you're okay with me erasing this split out right here, I'm going to go and I'm going to draw up Ohm's law. Is that okay? I'll leave it there. I'll write it over here as I was. Okay, so we want to find the voltage that's across this resistor right here for starters. And when we're looking for voltage drop across a specific resistor, so we're looking at resistor 1, typically we write something to the effect of V1 or VD1 for voltage drop, but I think it's simpler just to write V1. V1 is equal to the current, which we know is 1.3 times the resistance, which is 10 ohms. And that's going to give us the voltage that's running across this resistor right here. Does that make sense, guys? Okay. As long as, if you're ever stuck, just go back to Ohm's law. It's going to be your lifesaver in these situations. So 1.3 times 10 is actually 13. So there's, across this resistor right here, we actually have 13 volts right here. And we consider this a junction, and there's an entirely separate or different amount of voltage running across this resistor right here, this 5.38 ohm resistor. So there's two ways you can do this. You could draw out exactly like we did V2 1.3 times the voltage, or excuse me, the resistance value in ohms, or we know that 20 volts is the original voltage source. And we are losing 13 volts across the drop of R1, meaning there's 7 volts remaining to go through any other resistance that might be in the circuit. But there's only one resistor left in the circuit. So we don't even need to do any math to recognize that 7 volts is dropping across this resistor. But I don't want you to take my word for it. We can do the math if you'd like to. Can somebody punch up for me 1.3 times 5.38?
6.994.
6.994. So 6.994. And let's see, that's 7 volts. It's approximately 7 volts, give or take. We got a funky little 3.8 to contend with there. So that's consistent. I'm sorry, what was the question, Justin?
You answered it. I said, do you just round it up then?
Yeah. Yeah, typically we like to adhere to 7 points of accuracy, so 7.994, yeah. So 7 volts. So I mentioned in a couple of the lectures previously that a lot of this stuff is based around the concept of balance. And we know that all of our voltage source is going to get used up amongst all of the resistances that are available. If there was another resistor here, let's say right here, I would go ahead and do the math. But because we only have one more resistance that we have to contend with, we know that 20 take away 13, it's going to end up being 7 volts. Damn close to it. At least within a thousandth of a volt, right? A millivolt. So we're good there. Okay. Any questions yet? I know we made a lot of headway between where we were last week and this next step. But do we feel good about being able to use Ohm's law to find the voltage drop across a resistor?
Yes.
Yeah? Okay, cool. Excellent. And please, I recognize that this stuff is extremely cerebral and your brain is working in multiple dimensions right now. If you want me to go back and re-explain something, please let me know. We'll stop and we'll back it up and we'll go through it again. Okay, so I'm gonna rewrite this particular branch. Let me highlight it. This branch AB one more time, but this time I'm going to split it out into the parallel circuit that we had previously. And I think it's going to start getting a little more simplified. So, oops. Let's say branch A shrunk it down to 1 resistor, and then branch B. That's a terrible resistor icon, so let's fix that. That's not much better. So we know we have this one line right here, this one AB branch actually represents 2 branches. It represents a parallel circuit branch. And somebody answer, is the voltage in a 2 branches of a parallel circuit the same or is it different like in a series circuit?
Same.
It's the same, exactly. So 7 volts is actually going through A and B. So we're one step closer to figuring out everything that we need. Now we need to see the voltage drop amongst what we have left to work with. I don't want to erase this far right one because I think that's got a lot of information. Can I erase the resistance value right here, this 5.38?
Yes.
Okay. Because we're going to split it back out. It's pretty much going to be not useless, but it's going to be a little different. So this resistor right here that we're working with was actually, let's rewrite A again to the left, and we're going to get rid of it to some degree. It was 2 resistors. It was R2 and R3 at 15 ohms and 2 ohms. So we know that there's 7 volts going down branch A, which we can now get rid of this doppelganger here. And we also have established that the voltage is going to be different amongst the different resistors in a series circuit. So I'll let you guys tell me how you want to do this. Do we want to figure out the voltage drop across these guys right now, or you want to come back to it later?
You need to do it now.
Might as well. Okay, sounds good. All right, I'm going to move this branch B off to the side, and we're going to come back to this in just a moment because it needs to be blown up a little bit. So let's get this out of the way so we have some room to work. All right, so we have Ohm's law to work with. So we've got resistors 2 and 3, and we want to see the voltage drop across both of these resistances. So that would be the equivalent of, I think I want to do something else before we move into this. Can we take a quick segue? Because I don't think we've got the current to be able to solve this. Because we need the current for this branch and for this branch. But when we're talking about parallel circuits, the voltage may be the same, but the current is different. So let's take a look at this in greater detail. I'm going to collapse these again and we're going to come back to them. I don't want to obfuscate the problem. I believe this was 17 ohms. Okay. We've got 1.30 amps that was leading into these two branches. And we need to separate these guys. So typically we work in the realm of VIR. But if we want to know the current, we kind of have to throw it up. We have to go I is equal to V over R. And the way I got that before I get too far ahead is we're trying to get the current that's going through this branch. So we need to isolate I. So what I'm going to do is I'm going to divide R on one side of the equal sign. It's going to cancel out. Then I'm going to divide R on the other side. So our equation to figure out what the current is going to be I is equal to voltage over resistance, or voltage over resistance is equal to I. So I'm going to rearrange this. Are we good with how I isolated I for current? Okay, cool. I'm going to rewrite this. I is equal to V over R. And we're going to do each one of these branches one at a time. I'm going to call I, just for giggles, we're going to call I1 branch A, and we'll fill in what we need to know. So we don't know the current, that's what we're trying to figure out, but we do know 7 volts is going to be in the numerator. And the resistance on this guy is the 17 ohms right here. 17. So can somebody let me know what that comes out to?
0.411.
0.411, okay. 0.41. I'm just going to cap it at 2 points of precision. So we'll call this one 0.41 amps. So it was 1.3 amps that was going into, if I could, I'm basically just separating these just to have some space to isolate them. It was 1.30 amps going in. But at this junction, we've got 4.41 amps going down this branch. Let's do the exact same for branch B. I'm just going to call it I2, still 7 volts. And what was our resistance value here? It was 7.88 because it was the, yeah, it was 7.88 ohms. It was 1.88 plus 6 ohms for the series. For let me highlight it for you guys. This right here combined with 7.88. So let's go 7.88 ohms. All right, can somebody punch that in there so we can see what I2 is?
0.89.
0.89 amps. Okay, shits and giggles. Somebody add 4.1, 0.41 plus 0.89 together for me.
1.3.
1.30? Huzzah! Okay, good. So, as you can see, this 1.30 amps split between 4.41 amps and 0.89 amps. And this is part of Kirchhoff's current law. What goes out of a junction must equal to what goes in, and vice versa. What goes in must equal what comes out. So we know we're on the right track because we've added the two different branches of current and they equal the 1.3 that went into it. Are our brains cooking right now? You can be honest. We're all good? We're good to keep going? Richie's like, I got this. All right. So I'm going to update our little map, which is getting very populated here. 0.41 amps is going down branch A. 0.89 amps is going past this part right here. All right, we're getting there. We're getting there. Okay. We've got that so far. The next thing we need to do is we really need to focus on branch B so we can separate that. If you remember, it was a single circuit and then a parallel circuit. So we need to get back to that so we can start plugging this stuff in. I need to clean up our workspace a little bit. I really appreciate the technology of a tablet, but it's very confining. So I am going to rewrite branch A. 17 ohms. Okay, cool. That way I can get rid of this guy. Alrighty. Let's see. This branch B, I'm going to try and respect the original schematic by making it kind of out like that. This was actually a single resistor, and then below that was a parallel circuit. But let's break that back out so it's two resistors. The parallel circuit will be one resistor, and the original resistor, which is R4 right here, will be its own. So let's do this. I'm going to rewrite branch B, which we had as one resistor right here, and we're going to go down to two resistors. This resistor will be called R4, and this one is technically R56 because it's a parallel circuit, parallel circuit that's been collapsed. The values for this guy are 6 ohms and 1.88 ohms. Okay. Let's recall what we have. We've got 7 volts still coming in, and we've got 0.89 amps coming in. Now we've got a few choices here. We need to establish, is the current going to be the same across all resistors, and is the voltage going to be the same across all resistors? But we do know that we're treating this as a series circuit. So what do we know about the voltage drops here?
They're going to be different.
They're
No,
gonna-
they're all the way through.
the voltage for the series circuit is going to be different, which means the current is going to be the same.
That's what it was.
Excellent, you got it. Yeah, a lot of this stuff is just repetition, and that's why I want to do these problems together and do a lot of this group work. Okay, so let's look at what we need to find. We want to find the voltage, so we can go back to handy VIR, and I'm going to say we're looking for voltage We'll call it V4 because this is resistor 4 we're looking at. And we're also looking for, we'll say, V5, comma 6 to straighten it out in our heads. If that's possible at this point, because we're so down the rabbit hole right now, guys. This is total matrix stuff. What's that movie where like there's a dream within a dream within a dream?
Inception.
That's the one. I feel like this stuff is Inception. Tell me if I'm wrong, though. All right. So our current is going to be the same. We know 0.89 is going to be the value for both currents, for V4 and V56. We know that the resistance is what changes, because this is a series circuit, and it's 6 ohms and 1.88 ohms. Would somebody do me the honor of punching that in for me so that I can figure out?
V4 will be 5.34.
5.34. Okay. And then what's V56 going to be?
1.67.
1.67 volts. Okay. Well, it's 5.3.
Did I do that wrong?
No, you're doing it right. I'm just trying to figure out what the point of precision is, because if we add these up, ideally it should be 7 volts, but it's probably rounded up somewhere to go 5.34. So I'm going to leave it, I'm going to knock it down to 5.33, just so we can keep the points of precision, because ideally if we were to add these two voltages up, we should get 7 volts, the 7 volts that went into it. But you're not wrong. It's probably like 5.339 or something like that. So we'll go 5.34-ish. Let's do this. Ish. All right. So now that we have the voltage drops across both of these two sections, these two resistors, now we can feel comfortable expanding this final parallel circuit. Are you guys starting to get a sense of accomplishment for like how gnarly of a compacted problem this was, and you were able to break it down and then expand it and then like break it down again? I just want you guys to appreciate what you're doing here.
When I first saw it, I was kind of scared, but now it looks good.
Okay, good stuff. Most of this becomes clerical in nature. I mean, you have all the tools. You obviously know what you're doing. It's just keeping it straight as you go through it. All right, so I'm going to take this B branch right here and I'm going to rewrite it in its more original form. It kind of came out like this, and then there was a little resistor here, and then it branched out like this. Yeah, I feel like my resistor icons are getting worse and worse by the minute, but that's fine. So 6 ohms is going through here. We've got 0.89 amps still going through here, and then we have 5.33 volts here. What just happened? Come on now. But once we get past this resistor right here, this guy right here, this entire section actually has 1.67 volts going through it. And you guys see how that's coming about. It's because we had them identified as one resistor. We collapsed it. So when we exploded it back out, it's like this entire section, this sub branch right here, has 1.67 volts going through it. Does that make sense? Okay, cool. So here's another point that I want you guys to note. This resistor right here, this one which was R4, it had 6 ohms of resistance, and thus the voltage going through it was 5.33 volts. This section that we're talking about right here, this is R56, was 1.88 ohms of resistance. Much less resistance in the circuit, but also much less voltage as a result. Remember I was saying, I think back in week 2, week 1 even, we were talking about this concept of like a balance. We've got more resistance, we have more need for voltage, we have more pressure because that resistance is becoming friction in the circuit, and vice versa. There's less resistance in this section of the circuit, therefore less voltage. I just wanted to point that out really quickly. Okay, so going into this branch, I'm going to rewrite this a little further down so we have more room for notation. Guys, I know we're 10 minutes over, but we're so close to being done, I just want to knock it out for you guys. Are we okay with that, or do we want to pause?
Let's keep going.
All right,
Let's say continue.
All right, let's keep going then. Okay, so going into this section right here, we have 1.67 volts. We also have 0.89 amps. Now, a parallel circuit, we come to another crossroads. Is the voltage going to be the same across each of these branches, or is it going to be different? And is the current going to be the same across each of these branches, or is it going to be different? Who wants to take this one?
Wouldn't the current have dropped through the resistor, so we have a different current going through that?
All right, so let's look at this step by step. When we're going with a series set of resistors, the current is the same, but the voltage is different. And now we're looking at it parallels, right? We're taking two different avenues that the electrons, that the flow of electrons, not the pressure, but the quantity of electricity can take. So that would be the current will be the same or different through each branch.
The current will be different, although the voltage will be the same.
Exactly right, Christian. That's right on. Exactly. Remember, I think we use the analogy of like the river mouth. You have the pressure that goes into like a tributary where it like branches off into two different parts. That pressure is going to be the same, but those could be different size tributaries, so that the current will actually be the quantity of water going through each tributary will be different. So let's figure this one out. We can rewrite this to say that 1.67 is going to be going on through both sides. Voltage. The original resistance on this guy was 3 on this side and then 5 on that side. So we have the resistance for each branch and we have the voltage for each branch, but we do not yet know the current. So we can break out Ohm's law and get that bad boy. V is equal to IR, but we're looking for the current, and that's what we want to isolate. So first step into isolating the I, the current in VIR, in Ohm's law, is we're going to divide by R on both sides.
Yeah.
Excellent. Okay. I know we're getting tired. We're almost there. Hang in. Final push, guys. So we know that our formula that we're looking for is I is equal to V over R. I'm going to rewrite that as I is equal to V over R. And since...
Then you do it on the other side, right? Oh, yeah, never mind. Yeah.
Well, let's go with this. Let's see. I'm going to name these guys just so we can put values in there. I believe this was R6 was over here, and R7. I think that was right. Yeah, it was right here.
So for our, yeah, I think so.
Yep, you got it. Okay, so I'm going to call this I6 because this is corresponding to this resistor, R6. I is equal to the voltage being 1.67 volts over 3. Can somebody hammer that out for me real quick?
0.55.
Was that 0.55?
Yes.
It's 0.558, so I rounded it to 0.56. It
That'd
worked.
probably be smart because the next one, never mind. Yeah.
Okay.
That-
Let's go. We'll go with 0.56. Let's do that.
Yeah, 0.56 will make the adding up for the next one perfect.
Okay. All right. So I7, because we're looking at this branch right here that has resistor 7 on it, and our voltage is going to be consistent because we're dealing with a parallel circuit, and 5 ohms of resistance. Is this getting in the way? Let me move that guy.
I have a question.
Yes, please.
You know how like you on the first one where like you just automatically solved for voltage? 'Cause it was
Yes.
just one. Can we do the same thing here technically?
Yes, you
To
can. That is a great question, and that's Dustin. Was that Dustin that asked that one?
yes. Yeah.
Yes, that's 100% correct. Yes, and that's I kind of most people want to avoid that, but I want you to know that in your tool bag, you can cheat. It's okay. If you if you know you can solve for it, I say go for it. But if you're not sure, you can go through the equation, and if it doesn't jive, then you know you made a mistake. But that's 100% correct. So really quickly, let's do the calculation so we can add it up and see. What's 1.67 divided by 5?
0.33.
0.3?
3.
0.33? All right. And does that equate to the 0.89 that we had coming in at the top of the circuit? It does.
Yes.
That's 100%. So great question. Yes. The resounding huge, absolutely true. Yes. So that's it. And now we know that uh, we're getting a little crowded in here, but 0.56 amps are going down this branch. We don't need to put the voltage in here because we know it's going to be consistent. And 0.33 amps is going down that branch. So you figured it out. You literally nailed every drop, every component, every piece of wire, and you essentially know every value that's going through it. But here's something that I want to point out. So let's say I'm gonna erase branch A really quickly, this section right here. Yeah, let's do that. I might regret that, but let's go fast and loose, and then I'll cut you guys loose. I'm sorry for holding you on so late. So this is the bottom part of branch B. I'm talking about this part right here. I'm going to rewrite this. And I'm just looking at the amperage. 0.56, 0.33, and it came in at 0.89 from the top. This is actually going to come back here. I ask you, guys, what's the amperage value from this junction onward?
0.89.
Yes, yes. 100% correct. Exactly. I want you guys to start to see these conceptual balances, right? This yin and yang, and like it's very philosophical when you start looking at it. Like these circuits they like break off and they branch off, and there's these proportions, but they always come back to this succinct, very simplified balance at the end. If we were to look at, I'm looking right here at the top right. The current, whatever the current going in is, we'll say its value Y, right? It might branch off to a billion different subsets of whatever's going on. But when it comes back around to the negative terminal, it's going to come back to Y in a perfect loop, right? In a loop. It's going to spread, it's going to do, like the electricity is going to go in a million different paths, and it's going to go to the path of least resistance and go through resistors, it's going to go through components, and it's going to contribute to all these different sections in the circuit. And then when it comes back, it's going to come down to exactly where it started. Whereas here's the flip side of this coin. The voltage, it starts out strong. It starts out at 20 volts. But as it goes and drops through each component across the entire system, it's slowly getting used up. The potential, right? The the maximum potential that the circuit had is slowly getting shed as it goes through each different resistance drop in each different component until he comes back to the very end. And at that point, if you were to take a measurement, the voltage would be 0 volts. It's like this sublime reckoning that happens across the entire circuit. And I just wanted to point that out to you. So if you guys can keep that in the back of your mind when you're going through these and you're starting to recognize that electrons, they're not the electrons aren't getting shed, but the current is getting shed as it goes through the system, as it's being used up. The voltage is going and getting used up through the components, and there's this synchronicity to the entire thing at the end of the day. So that's it. I apologize for taking you a whole 20 minutes beyond what I wanted to. I thank you so much for your grace, and I appreciate your staying in it, even though you're tired and you want to go back to your families. Any questions for me before we sign off?
Thank you. I appreciate it for you showing us all this. And
No. Thank you, guys. You are all awesome rock stars. If you can do this, you won't have a problem for any part of the class. Okay, this is as deep and as dense as we need to get, and you've got all the tenets, you've got all the tools right here. So thank you so much. If you have any other questions, feel free to send me a message afterwards, and then Monday we'll set up that second live lecture, and we'll continue with the Wednesday lecture. So thank you, guys. I really appreciate it.
thank you. Have a good one.
You too. Bye, guys. Have a great weekend.
Bye. Thank you.
Bye.
Have a good night, Justin.
Thanks, you too. Thanks, John. All right, that's a wrap.